Hello, everyone. Thank you for coming to our May online lecture event. We are the Center for Climate Science and Engineering at the University of Toronto. We host monthly guest lectures. My name is Mohamed Jolier. I'm the CSE manager. Today, we are pleased to feature Dr. Michael Barbato from the University of California, Davis. First of all, I'd like to go through the land acknowledgement. We wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still home to many indigenous people from across the Turtle Island, and we are grateful to have the opportunity to work on this land. For those who haven't attended our guest lecture events before, the CSE is a research and education center within the Civil and Mineral Engineering Department at the University of Toronto, and it was established in 2019. The CSE consists of a diverse and multidisciplinary team of faculty members who collaborate on interdisciplinary research at the intersection of climate science and engineering. Our center's director is Oya Merjan, and she focuses on structural analysis. Daniel Poulsen focuses on life cycle assessment. Ahmed Ibrahim works on hydrologic variability and processes. Karen Smith focuses on atmospheric science. Mohammed Bashir focuses on hydrology and water resource systems. Paul Kushner looks at climate dynamics. Sam Markov from the University of California, Merced, focuses on sustainability and resilience. And then me, the CSE manager. So one of the primary initiatives undertaken by the CSE focuses on providing education in climate science and engineering. We have developed and launched 2 graduate-level courses at the University of Toronto. Additionally, we have created 8 online learning modules that are now accessible for use across higher education institutions in Ontario. We also design and run 2 courses through the University of Toronto's Deep Summer Academy for high school students. Furthermore, our faculty members are engaged in collaborative research projects at the intersection of climate science and engineering. Also, our team organizes outreach activities just like this one, where we invite the public or university community to give a presentation on topics that are aligned with the mandate and vision we have at this center. Now, I'd like to introduce today's guest lecture speaker. Dr. Michael Barbato is a professor of structural engineering and structural mechanics in the Department of Civil and Environmental Engineering at the University of California, Davis. He is also co-director of UC Davis Climate Adaptation Research Center and director of the Citrus Climate Initiative. He received his master's and PhD degrees in structural engineering at the University of California, San Diego. Dr. Barbato is an expert in both traditional and innovative construction methodologies and materials, with particular emphasis on near recycle and green materials. He is active in the development of performance-based methodologies in earthquake, wind, hurricane, and wildfire engineering, as well as in multi-hazard applications. Dr. Barbato's research also embraces nonlinear finite element modeling and analysis of structural systems, random vibration theory, structural liability analysis, multi-hazard assessment and mitigation under current and changing climate conditions, and life cycle cost optimization of resilient or sustainable structures subjected to multiple hazards. He is the author of more than 200 technical publications and has received numerous awards. Dr. Barbato is also an American Society of Civil Engineers Fellow and actively contributes to various ASC committees. He is going to give a presentation on advanced earthen construction for climate resilience, affordable, and sustainable buildings. Dr. Barbato, welcome. We are very excited to learn more about your research. I am passing it over to you. Now, the floor is yours.
Thank you very much. Thank you for inviting me. It's a pleasure to be here and have this opportunity to talk about some of the research that we are performing at UC Davis and with our collaborators across all of the United States and in Europe. Before I proceed, just want to make sure that you are seeing my screen.
Yeah, it's perfect.
Okay, perfect. So also thank you very much for the nice introduction. As I was saying, this is a presentation on current research that we are performing at UC Davis and is focused on earthen construction, a typology of construction that we see as a modern solution to the current problem of having affordable, sustainable, and safe housing and low-rise buildings across not only US, but hopefully the world. And I will start by introducing this type of construction with the motivation why we are working on these advantages and challenges that are encountered by using this technology. And then I will present two researches that we have completed, one on the feasibility of using compressed and stabilized earth block construction, and another on the methodology of modeling this type of masonry by using finite element techniques. And then I will touch upon some ongoing work that are focused on wildfire resilience, wildfire emissions, and 3D printing, which are a little bit newer in terms of the research that we are performing. They're not yet a complete body of work, but they can give us an idea of where this technology will go. So let me start by introducing what earthen construction is. Fundamentally is going back to the solution of building structures by using mainly soil. This is one of the most ancient and sustainable building technologies. It has more than 10,000 years and is still widely used around the world. It is estimated that about 30 to 50% of the entire world population actually lives in earth-based dwellings. You can see in this picture on the bottom, the orange color corresponds to the places where earthen construction have been found across the planet. And then I have some examples of ancient constructions made by using different technologies based on earthen construction. So it is something that is ancient. And it has been used in different flavors, typically cob, rammed earth, and adobe across the world. These three technologies are slightly different. In cob, fundamentally, you have a slurry of soil that is layered to build walls. In rammed earth, you are using a machine to compact the walls by ramming into them on both sides. And in Adobe, we have probably the most known technology that is fundamentally a masonry done with bricks that are dried under the sun and then used for construction. Obviously, these are historical technologies. They are important a lot for conservation of existing construction, but there is also a modern flavor to it. And a modern flavor is done by different technologies based on earth blocks. The three different flavors are compressed earth blocks, where the soil is mechanically compressed to increase the strength of the different blocks that are done without any firing, but only with mechanical energy. Stabilized earth blocks are obtained by adding a chemical stabilizer, typically lime or cement, to increase the durability of the block. And then compressed and stabilized earth blocks, which is the technology that we are developing at UC Davis, working on at UC Davis, where the two technologies are put together to have a block that is at the same time mechanically sound and strong, but also durable under different weather conditions. And again, you can see different examples here, even modern examples of usage of the compressed and stabilized earth block technology that are, again, very resilient type of structures. So why are we going back to something that is so ancient and trying to give a modern flavor to it? There are actually several reasons. From one practical point of view, it's the shortage of housing in US and in other countries, particularly the shortage of affordable housing. And this material is a locally available material that is extremely cheap compared with any other type of construction material. In a larger view, there is a big need for new housing. It is estimated that more than 2 billion new houses will be needed worldwide in the next 80 years, which is a huge amount of housing. This is both for the increase in population, but also for the improvement of living conditions. And if we are looking at this need, we need to come up with the technology that is also sustainable. Otherwise, we are not going to be able to reach our goals in terms of reduction of our carbon emissions. So there is a need, and this material could be a solution. There is also an interest from a purely engineering point of view. This material has been used for a very long time, but has not been studied as deeply as other industrial materials. It has a very different mechanical behavior than that of ordinary masonry, and we will see that in the next part of the presentation. And the existing numerical methods that are used for ordinary masonry do not work well for this type of construction. There is also a problem of lack of standardization and a very limited understanding of the performance and the reliability of these structures, which is something that is needed if you want to have an adoption at scale of the technology. So, what are the advantages? But the first one is the material is affordable and locally appropriate. Here there is a USGS map of the classification of the soil across the United States. And then the triangle of classification used by the US Department of Agriculture. If you look at the region included in the red line, this is the composition of soil that can provide earth blocks that are performing well from a mechanical point of view without any addition of chemical stabilizers. If you look at the region included into the dashed yellow line, you actually see how this composition can be expanded by using a moderate or small amount of chemical stabilizer. When you map it into the United States map of soil, you actually find that almost everywhere, except in the delta of rivers where the amount of expansive clay is very high, you can find soil that can be directly used for construction of structures by using earthen compressed and stabilized earth blocks. The fact that the material is locally available makes it extremely affordable. There is a reduction in cost on transportation, and obviously whenever there is that reduction, there is also an additional advantage of reduction in emissions. In addition to that, the structures that are made with this material are naturally resistant to fire, mold, rot, insects, pests, termites. And that's because it's fundamentally against soil, and these type of actions cannot damage soil. In terms of additional advantages, something that is very important is that this material is a breathable material, is able to maintain an healthy relative indoor humidity by taking out from the air excess humidity when the indoor air is too humid, and then releasing it back when it gets too dry. And so it is a natural way of keeping indoor humidity into a healthy range. It also doesn't release any volatile organic compounds that can be bad for human health. And then it is eco-efficient and sustainable. On one side, of the side of operational energy, it has been shown that it can produce a 30 to 70% savings in heating and cooling compared with a light-framed wooden house, depending on the climates where it is built. But also, it has a smaller embodied energy than other conventional masonry materials. And here you can see the equivalent CO2 per ton of material in kilograms of earth blocks compared with the concrete blocks, ceramic blocks, fired clay blocks, and aerated concrete blocks. So the embodied energy is lower and the operational energy is lower. In addition, recent research, some of which were performed also by my research group with collaborators, has shown that this type of construction has a good resistance to hurricanes, tornadoes, and with the appropriate reinforcement, also earthquake actions. So all of these nice things, there are obviously also challenges. Otherwise, we would already see the type of construction used in modern construction everywhere. So one issue is the high variability of the mechanical properties. This high variability is coming from the fact that the material is a natural material, and thus there is less possibility of control than industrial materials that are produced under very controlled conditions. The result is that there is a higher dispersion whenever mechanical testing is performed. There is also an intrinsic problem with any type of earthen construction that is a pure durability in wet climates. And there is an historical test that was done on a rammed earth wall that shows how the humidity from the ground coming up and down through capillarity can produce damage in the walls. In addition, it is a masonry product, so it has an intrinsic characteristic of brittleness, which fundamentally means it reaches its peak strength and then it breaks really, really fast. In addition to these technical issues, there are some other issues that are beyond technical. One is that is labor intensive. So that means costly in places where labor is expensive. And the worst issue, even though it's not technical, but is more cultural, is the perception that earthen construction is a substandard soil when you substandard choice when you compare it with other modern industrial type of construction. But this perception is really driven by the poor performance of non-engineered earthen structures in different parts of the world, for which I would like to add that when a structure is not properly engineered to sustain the loads that will be applied during the lifetime, any type of material will perform poorly. So there are technical issues and there are cultural issues that need to be addressed. Here, to give a better idea of what we are talking about, I'm showing some of the blocks that we can produce by using soil. So these are compressed and stabilized earth blocks of different shapes. You are seeing in the video some of our students that are building a block, fabricating a block using our first version of a modified Simbaran manual machine for making blocks. As you can see, quite laborious process. However, you can also see in our picture a machine, an Auran press, a semi-automatic hydraulic press that makes this work significantly faster and less laborious. In our original Simbaram, we were able to build about 30, maybe 40 blocks per hour. by having a crew of students that was exchanging the position. With our hydraulic press, we can produce between 300 and 400 earth blocks in the same hour of time. Now we know what we are talking about. I want to present a couple of studies that we have completed several years ago. One on the feasibility of using these houses, and I will start with that. This was a feasibility study that was performed in the U.S. Gulf Coast, in the U.S. Gulf of Mexico. Precisely in southern Louisiana. This was a study that was trying to address the need for affordable hurricane-resistant housing in southern Louisiana in the aftermath of Hurricane Katrina. There were about 400,000 low-income households in need of housing. And the place was particularly bad for this type of construction. One, because the soil quality is poor. Again, we are close to the delta of the Mississippi River, a lot of expansive clay. The climate is hot and wet, which is also a difficult climate for earthen construction. And then we have high wind loads coming from the frequent hurricanes that affect that region, and we needed to keep the cost low. In addition to that, we needed also to have solutions that were culturally appropriate so that in terms of adoption, people would feel comfortable in using these type of houses. And we investigated the structural feasibility, the architectural feasibility, and the economic feasibility of these homes. We started by identifying the soil. We took soil that were around the campus of Louisiana State University, so along the Mississippi River. If you look at the USGS soil texture triangle on the right top of these slide, you will see that all of the soils that we found were outside of the optimal region identified here by this blue line. But most of them were inside the region where usage of stabilization, chemical stabilization could be adopted to build this type of construction. So what we did, we used the cement to improve the mechanical strength and the durability of this material. And we started with the block made with only soil, and then we added cement, 3% of mass of the dry material, up to 12% cement. And then we performed the flexure tests and compression tests and durability tests, and the compression tests were performed both in dry conditions and in wet conditions. What we found is that most of our composition had a sufficient modulus of rupture, the one that is obtained from the flexure test that is really measuring the behavior intention and the brittleness. Then with at least 6% cement, we had a sufficient compressive strength. And then in order to achieve a compressive strength under wet condition as that is suggested in the literature, we actually had to use a relatively large amount of cement that are 9 and 12%. And again, this is mainly due to the fact that the soil was not the best soil to start with. The first issue that we wanted to identify is how do we protect this material from the wet, humid conditions of southern Louisiana. Here you can see the results of a test that we did by building a small wall outside of the LSU campus where one side of the wall was protected with a composition of soil and cement similar to the one used for building the blocks, and the other was left unprotected. And you can see in the unprotected side, very soon, this is a 6 months test during which we actually had two tropical storms. So it was short but pretty intense as a test. You can see on the side that is left unprotected, the mortar between the blocks is washed away by the heavy rain and wind, and this produces some mechanical damage to the bricks that are not anymore fully connected. On the other side, the one protected by our soil cement, let's call it stucco, although it's not a stucco, but protection, a layer of protection, we actually see no damage. Not only that, but actually when we finished our 6 months of testing, we dismantled carefully the blocks from both sides, and we retested them for both flexure and compressive strength. And what we found was that the side that was protected actually ended up being stronger than the initial strength obtained by the blocks or from the blocks when they were before they were put in place. We performed our further investigation of engineering performance of these houses subjected to wind actions. And we actually came up with this graph that allows us to design the needed thickness of the wall in order to allow design according to AC7 for the different wind speeds at different locations in Louisiana. If we look at this graph on the horizontal axis, we have the design wind speed from AC7. The vertical lines are the wind speed corresponding to different towns in southern Louisiana. The horizontal lines are the mechanical strength of the blocks with 9% and 12% cement. And then the other colored lines correspond to the different thickness of the wall that are needed to sustain each of these design wind speed. And so, for example, if we want to design a house for New Orleans for New Orleans that has 65 something meters per second wind speed for design, we can use a 9% cement block with a thickness of 35 centimeters, the purple line, or we can use a 12% cement block with a thickness of 30 centimeters, the red line. So this is a very quick way of designing the dimensions of our walls and selecting the proper amount of cement that needs to be used to produce the bricks. We also did an economic feasibility study, and here we devised a new technology for building these structures that are typically built by using brick and mortar approaches. But we developed a technology based on interlocking blocks that can be done without having to use mortar to transfer the lateral loads across the different blocks. And we compared the cost of this new technology, the interlocking compressed and stabilizer blocks without mortar, the ordinary CSEB with mortar, light frame wood construction, which is typically what is used in 95% of the housing in the US, and then fired clay bricks and concrete blocks. Fundamentally, the difference in cost is coming from the wall construction. And we found that by using an interlocking construction without mortar, we actually were able to match and even be a little bit lower than the economic cost of building a light framed wood, and this comparison was done for a reference shotgun prototype house of 1,000 square feet. So there is actually the possibility of building these houses at a lower cost than the current technology of light frame wood. Given this result, we started investigating how to predict the performance of this type of construction. We started developing a macro modeling approach for finite element modeling of these earthen construction. Here, just to give you an idea, there are two main the micro modeling approach that are used for masonry. There is the simplified micro modeling approach where the masonry units and the mortar are really modified in order to reduce the computational cost. Fundamentally, the mortar layer is reduced to a zero thickness joint interface, and the masonry units are expanded to account for half of the thickness of the mortar layer. This allows to reduce significantly the computational cost of the problem because all of the nonlinearities can be fundamentally attached to the mortar joint interface. And this is valid as long as the failure modes of the system are all happening along the mortar, which is typically the case for ordinary masonry, where the mortar is typically the weak spot in the structure. However, there is also another approach that is less used because more computationally expensive, that is the detailed micromodeling, where all of the different components, which means the masonry, the mortar, and the interface between masonry and mortar, are modeled separately and independently. And this is called a detailed micromodel approach. Again, in the literature, you will find very few applications of this methodology because fundamentally for ordinary structure, it is more expensive but gives similar results as the simplified micromodel. And I'm going to actually show it here. So by using the detailed micromodeling approach for an ordinary wall of masonry for which experimental data are available, represented by these black lines, we were able to model the behavior of this structure in a particularly well, I would say in a relatively accurate manner. You can see this blue line is our numerical simulations and how it compares with the experimental results. And also on the left side, you can see the development of the principal stress and the principal strain and the plastic strain, as well as the development of the cracking within the structure that again has a very good correspondence with the experimental results. So what we found here is that by using different flavors of the simplified micromodeling approach and of the detailed micromodeling approach, we were fundamentally obtaining very similar results. Yes, the detailed micromodeling approach is slightly more accurate for something than the other approaches, but fundamentally we are capturing the global behavior as well as the development of cracking in the structure, also by using the simplified modeling approach. So this would actually tell us, but why are you spending time in developing a detailed micromodeling approach? And the reason is for earthen construction, the mortar and the blocks have a very similar strength, which is very different from what you have in ordinary masonry, where the mortar is typically weaker. So the basic assumption of the simplified micromodeling approach is not satisfied. And this is shown here on the right by experimental results, where you can see that the cracking of the structure is not limited to the mortar. It generally goes through the blocks and the mortar, almost as if the material was an homogeneous material. So what we found is when we were using the simplified macro modeling approach, we were overestimating, even by a factor higher than 2, the actual strength obtained from experimental testing. You can see here the black lines corresponding to the triplet that is shown here. So they are kind of consistent and they are significantly lower strength than the one estimated with these other curves. So at that point, we had a very strong indication that we needed to do something different. And the something different was developing this detailed micromodeling approach, which actually was able to capture both the global and the local behavior of these new masonry extremely well. This is the yellow line corresponding to this new modeling, as well as the principal stresses and the principal plastic strain in the wallette, which the light color corresponds to where the cracking is developed. You can see that even visually there is a very good correspondence with the experimental results. So as a conclusion, this type of modeling, although more expensive, is necessary in order to capture the real mechanical behavior of earthen construction. Now, these were two projects that were completed. I'm going to move on something that is still ongoing, but extremely exciting. On one side, the use of earthen construction for homes that are fire resilient. And here you can see why we want to use this material for houses that are built in the Walden urban interface. And that is because fundamentally earth blocks are non-combustible materials while we are building with wood right now, and wood obviously burns. Not only that, but you can see that fundamentally, even under a propane torch at 3400 Fahrenheit, the only effect that you can see on our blocks is a change in color. And we tested our blocks in a furnace for a very long period of time at very high temperature. And so I'm going to show actually some of these results. We fabricated 60 blocks with the Simvaram using a soil that was collected from the town of Paradise in California, the town that is unfortunately famous for being completely destroyed by the Camp Fire in 2018. And with that soil, a 9% Portland cement, we fabricated these blocks. Then we divided them into 6 different groups that were subjected to different temperature in a furnace. We left 10 blocks at room temperature, and then 10 were tested at 200 Celsius, 400 Celsius, 600 Celsius, 800 Celsius, up to 1000 Celsius for a prolonged period of time. After these, we took the blocks, we tested them first on a 3-point flexure test, and then we took the 2 halves obtained from that test, we trimmed them, and we used them for compressive strength in dry and wet conditions. So what we found? From a visual inspection, the first thing that we saw is the change in color that we showed also in the previous video. Fundamentally, the color changed from a brown that is typical of unfired clay into the red that is actually more typical of fired clay bricks. And you can see here how this is proceeding from the outside, and with the 1000 Celsius, it goes through the entire depth of the block. These are the half block after testing for flexure. In terms of experimental results for the 3-point bending test, what we found is that there was a reduction in bending strength with a lot of variability, so barely significant from a statistical point of view, but absolutely not negligible. However, even at 1000 Celsius, we found that the final modulus of rupture is still above the minimum requirement of the New Mexico Administrative Code, that right now is the only code in US that really allows construction using this type of material. We actually found that the reason for this reduction of strength was the high amount of cement. So we are investigating ways of making these blocks more resilient to fire and more sustainable. However, there were other things that were also interesting. So we did these compression tests, and both in the dry compression test, again, there is a slight decrease of strength from 200 to 600 degrees, and then a stabilization. But in reality, this reduction is non-statistically significant. So from a statistical point of view, there is no reduction in strength for the dry conditions. However, for the wet compressive strength, and this was a little bit more surprising, although in hindsight it made really sense, we found that the strength is increasing actually significantly. We went from about 2.5 to almost 8 megapascal of wet compressive strength. And that is because we are fundamentally with fire transforming our unfired clay blocks into fired clay blocks, which are known to be equally resistant under wet conditions. So the material actually got stronger. And so all of these is kind of indicating that the material can be actually used very effectively to obtain a structure that will not burn under fire, not only, but that will be still keeping the structural integrity to be reused even after fire. Another thing that we are investigating right now is assessing the wildfire emissions from housing. And I will go very quickly through this because I see that I'm close to the end of my time. But the idea is to get the information about the houses, the burning conditions, and the emission factors from controlled lab experiments to estimate the CO2 equivalent produced by a house built with different technology that is burning. And then when we combine this information with the life cycle CO2 equivalent, we can now estimate their contribution to emissions. This is part of a closed circular economy approach to our housing, where we need to include also the effect of wildfire emissions if we want to really have a good estimate of the emissions that are produced. So in this part, I will just focus on the estimate carbon production from the burning of the houses. And the same approach can be also used to assess particle matters and other pollutants that are dangerous for human health. What we did was take the design of houses that were used for reconstruction in Paradise, evaluate all of the materials that are used for the construction depending on the size, and then evaluating it for different technologies. In particular, we considered three different conditions. A light frame wood construction that is non-compliant with Chapter 7A of the California Building Code. This is representative of older structures that are not in compliance with the new building codes. A same light frame wood construction that is compliant with Chapter 7A. And then an earth block construction, which is also compliant with Chapter 7A. In terms of costs, we found that the non-compliant house, as expected, is the cheapest, but the earth block construction, due to the implicit resistance of earth blocks, is actually can be actually built at a lower cost than the California Chapter 7A compliant structure. And then we made a bunch of assumptions because we are still calculating the emissions factors from small-scale lab experiments. We assume that these results can be scalable at larger scale. We did this analysis only using the mean values of the emission factors, and we made the assumption that the fire is burning at 1000 Celsius. Some elements are still missing, like paint. We don't have yet the data, and some other quantities that are small or not yet available were also excluded. For some materials for which we evaluated the embodied carbon, we used the results that were available in the literature. And so what is that we were trying to get? We evaluated the emissions in terms of carbon and methane, and then for each different structure, we evaluated what were the emissions in terms of burning. When we put it together with the life cycle analysis, we have that the earth block construction has an embodied energy that is fundamentally the same as a wooden house. But if we include the effect in terms of emissions of burning of the house, for the earth block construction, all of the burning and emissions are coming fundamentally from the content and things that are added, while the entire structure will burn for wooden houses. And so you can see that the end result of this is that the emissions of an earth block construction are less than 1/2 of the emissions of a light frame wooden house, with the difference that you still have a house at the end of the day, while for the wooden house there is only ash. Another things we are very excited is the use of 3D printing with soil-based materials. This is really a very preliminary result. This is our first successful print. We are using now a different tool to build it. We've been able to build walls that are 6 feet wide. So very excited about this. I'm going to wrap it up. I think my time is finished. So what are the results of our research? The Earthen masonry represent an affordable, safe, and sustainable techniques that can be used for building houses and low-rise buildings. These houses can be designed to perform properly according to modern codes and standards under seismic, hurricane, and tornado actions. We have also shown that detailed micro modeling is needed in order to accurately predict the performance and mechanical behavior of this type of walls and structures. Compressed stabilizer block materials can be used as a fire resilient construction material. that can reduce cost, increase resilience, and also reduce emissions. And then 3D printing of earthen material is a promising technology that deserves to be investigated. Let me finish by saying that earthen masonry, due to the affordability and to the fact that the material is locally available, has a great potential to address climate change, but also to produce economic development in an equitable manner, which I think is very important in our fight against the issues produced by climate change. Acknowledgements from everybody that has funded this research and collaborators and students. And with this, I'd like to thank you very much, and I'll be very happy to respond to any question you may have. Thank you.